Oh, hi there. Research for a different paper. Today we're going to be talking about LIM, the company that helped make Star Wars and Back to the Future possible. What do you mean that's IL?
The Latency Insertion Method.
Latency Insertion Method, or LIM, is a method of solving circuits using half time steps for calculation of voltage and full steps for the calculation of current. This can only be done when each part of the circuit has a method of latency to it. We can be sure this happens if there's a capacitor in parallel with resistors or inductors in series with resistors. We will calculate the voltage segments on the half steps and amperage segments on the whole time step. And that's the basis for LIM. So let's get solving.
When we calculate current, we calculate it over segments. An example segment is shown here, from I to J. The voltage at node I is VI and at node J is VJ. Calculating the voltage drop over this segment will give us the current I of IJ by dividing the voltage drop by the segment's resistance. This means that VI minus VJ equals LI times DI of IJ dt plus R of IJ times I of IJ minus E of IJ, which is any additional voltage source on the segment. To calculate the voltage at a node, we calculate the current at the node and multiply by the resistance. To do this, we sum the currents leaving the node and multiply by 1 over the resistance of the node. It's easiest to show this via a node to ground as we have here. This arithmetic gives us the negative summation of amperages leaving the node, which equals Ci times dVi dt plus Gi Vi minus Hi, where Hi is the current from the node's branches and G is the admittance of the node's resistance. We can visualize the order the calculations are performed in with the bar graph shown. I's are calculated on whole integers of the time step, while V's are calculated on the half integers of the time step. The calculation switches between I and V as we progress through time. From our previous equations, we can implement an approximation of dV dt and di dt. By assuming that the value of di or dV dt over the time step is equal to the n plus 1 value minus the n value divided by the time step. Implementing this approximation, we substitute the values in the equation and are left with a slightly modified equation. The equation is then rearranged in terms of V at the n plus 1 half time step, so it's easier to know where to begin our calculations as we are usually given a system's initial values. The equation for V of n plus 1 half is the node capacitance Ci times V at n minus 1 half divided by the time step delta t, plus Hi at time n, minus the currents leaving the node. This is all divided by capacitance Ci over delta t plus Gi. The equation for the calculation of current over the approximation does not need to be reorganized. We just need to know which V's and I's we need in order to evaluate the expression. The equation we will be evaluating is Vi at n plus 1 half minus Vj at n plus 1 half, which equals Lij times Iij at n plus 1 minus Iij at n divided by delta t plus Rij times Iij at time n minus Eij at time n plus 1 half. Using the equations we derived earlier, we can solve this example. Please note I've labeled nodes 1, 2, and 3 to make this easier. As you can see, section 1 to ground, 2 to ground, and 3 to ground, along with segments 1 to 2, 2 to 3, and 1 to 3. Below we have our givens. All the L's, C's, and R's have been set equal to each other, with a time step of 1 millisecond and an amperage source of 1 amp. First, we need to ensure that our time step is fast enough to make calculations of this circuit using an LIM approach effective. To do this, we need to know if delta t is less than or equal to the square root of L and C. You should use the smallest L and C's possible on your circuit to ensure that even the quickest reacting segments can be calculated appropriately. The initial voltages and amperages of the circuit have been set to 0 as well, just to make calculations that much easier. For our first calculation, we will use t of 0. This gives us V1 of 0 plus 1 half, or the first half step of V1, equals C1 V1 negative 1 half divided by delta t, plus Hi of 0 minus I12 of 0 minus I13 of 0, divided by C1 over delta t, plus G1. Now we have all of these values, and in fact I've plugged them in. Please remember that I12 and I of 13 at time 0 are both equal to 0. This gives us an initial voltage for V1 at the 1 half time step of 1/6 of a volt. We can use these exact same numbers and equations to calculate V2 and V3 at the 1 half time step. At t equals 0, calculating at the 1 half time step, we have calculated for 1/2 of delta t, or in this case, 0.5 milliseconds. Now that we've calculated V at the first time step, or V of 1/2, for V1, V2, and V3, we can calculate I through segment 1, 2, I through segment 2, 3, and I through segment 1, 3. Using the equation V1 of 1/2 minus V2 of 1/2, we can get the amperage for segment 1, 2. This gives us V1 of 1/2 minus V2 of 1/2 equals L of 1, 2 times I of 1, 2 at time 1 minus I of 1, 2 at time 0 divided by delta T plus R of 1, 2 at I of 1, 2 times 0 minus E of 1, 2 at time 1/2. Now we know there's no E source on the segment 1, 2, 2, 3, or 1, 3, so we can remove all of those from these equations. We also know that I of 1, 2, I of 1, 3, and I of 2, 3 is 0. Plugging in these values, we are left with only I of 1, 2 at time 1, I of 2, 3 at time 1, or I of 1, 3 at time 1 as the variables. For I of 1, 2, we can rearrange it so that I of 1, 2 at time 1 is shown to be equal to V of 1 at time 1/2 divided by L times the time step. This gives us I of 1, 2 at 1/30th of an amp. We can see that for I of 1, 3 this is also true, and for I of 2, 3 this is 0. Please take the time to do the calculations yourself to verify that what I have said is true. And now that we've calculated I of 1, 2 at time 1, I of 2, 3 at time 1, and I of 1, 3 at time 1, we can now calculate the voltage at the time step of 1, or the voltage is at the 1.5 time step. So V of 1.5 can be calculated using the values we plugged in earlier as 5/6 V1 of 0.5 plus 1/6 minus 2/30 times 1/6. Please forgive me for not writing this out longhand, but there's a lot of equations I've shortened to save time, paper, and my poor hand. We can also solve these equations for V2 and V3 at time 1.5, showing that these are both equal to 1/80 volts. Once again, I strongly encourage you to do these calculations by hand yourself so you can see exactly where my calculations come from, and you can see why these simplifications have been made on my part. Now with our voltages calculated at the 1.5 time step, we can now calculate our I's for the whole time step of team 1. This gives us I12 of time 2, I23 of time 2, and I13 of time 2. Once you write the equations from before and fill in all of the variables we've calculated already, these steps become quite trivial. At the end of our first time step calculation, t equals 1, we are at time 2 milliseconds. As you can see, this process can be automated quite quickly because it's just a bunch of simple calculations over and over again.
Thank you for watching, and feel free to share what you've learned.